Okay, let's try again. Okay, so if we know the Ka, now we can go the other way. We can use the initial concentrations, figure out our change using a variable, and then find Ka. We did this before in Chapter 15 when we found K sub c. Now, here's the chart I referred to previously on page 16. So keep that handy. It's a good place to look things up. And the one thing, this butanoic acid, but means 4 carbons. This is butyric acid. So same thing if you don't recognize it. Now again, we can make some of the same simplifications that we did before. First thing we can do is assume that the autoionization of water, the amount of hydrogen ion coming from water, is insignificant. And remember, water breaks down into a hydrogen ion and a hydroxide ion. And since Kw is 1 times 10 to the 14th, that means that the hydrogen ion and the hydroxide ion are 1 times 10 to the negative 7th. So that's going to be small and insignificant compared to the hydrogen ion coming from most of these acids. There may be some special cases where we have to deal with that, but not very often. And we can ignore the ionization of the weak acid. That was our assumption before, that X is small. And most of the time, we can get away with that when Ka is less than 10 to the negative 3rd. But for sure, we can get away with it when Ka is less than 10 to the negative 5th. So the first assumption is the concentration of the acid is big enough that we can ignore the ionization of water. And the second assumption is that the Ka is small, so X is small, and it simplifies our math. So now, if you flip to page 16.7, let's look at these combinations of concentrations and Ka values. So let's look at assumption number 1. Can we ignore the ionization of water? And assumption number 2, can we say X is small and ignore X? So for the first one, my initial concentration of the acid is 0.5 molar. My Ka is 1.5 times 10 to the negative 12th. Is the concentration here big enough that 1 times 10 to the negative 7th is small and I can ignore the hydrogen that comes from water? Yes, it is. Is X going to be small because Ka is small? Yes. So life is easier. Now look at this one. If my original concentration is 2 times 10 to the negative 7th, can I ignore the hydrogen coming from water? No, because it's 1 times 10 to the negative 7th. So we have to figure that in. Now, if the Ka is 10 to the negative 10th, can I ignore X? Yes. So here we have one assumption that works and one that doesn't. How about here, where I have 0.5 molar starting and a Ka of 1.5 times 10 to the negative 7th? Can I ignore the autoionization of water and the hydrogen ion? Yes. But can I ignore X in my calculations? No. And finally, when we have a concentration of 5 times 10 to the negative 12th molar, which is quite small, and a Ka of 3.5 times 10 to the negative 1, which is kind of big, can I ignore the water's ionization? No. And can I ignore X? No. So that's the problem we never want to solve in this class, right? We want to do these. And the other that aren't so bad is these are kind of the second level where you have to do the quadratic, but that's not too bad. Okay, so let's look at our first example of finding the pH of a weak acid using this equilibrium stuff. So we have acetic acid ionizing to make a hydrogen ion and an acetate ion. So calculate the pH, the hydrogen ion concentration, for a 0.1 molar acetic acid solution. You actually need to find H plus before you can find the pH. So we start off, I'm going to just be lazy and use the generic here, right? HA is H plus plus A minus. So now I know that Ka is equal to the concentration of H plus times the concentration of A minus divided by HA. So we'll go ahead and use that chart on page 16-16, and we look up the Ka. So you'll need this chart when you're doing your homework. It's 1.8 times 10 to the negative fifth. And that's a small enough Ka that we can ignore X. So now we'll prepare our ice chart, again, using a variable like we did back in chapter 15. So I have 0.1 molar for my acid. Originally, I have no hydrogen ion and no acetate ion. Now, this goes down by X, and these go up by X because it's 1-to-1-to-1 stoichiometry. At equilibrium, I have 0.1 minus X, X, and X. So this looks just like the problems that we did in chapter 15, and it's one of the easier ones because it's all 1-to-1 stoichiometry. So now we go through and solve, and if we do ignore X, always go back and check and make sure that that was an okay assumption. So we know Ka, 1.8 times 10 to the negative fifth is equal to X times 0.100 minus X. And we assume X is small, so then 1.8 times 10 to the negative fifth is equal to X squared divided by 0.1 molar. So now we rearrange by multiplying, so 1.8 times 10 to the negative sixth is equal to X squared. So the square root of 1.8 times 10 to the negative sixth is equal to X, and that's equal to 1.3 times 10 to the negative third molar. So now, when you look at this isn't algebra class, so you have to remember, you got to figure out what X means. And X here is representing for us the hydrogen ion concentration, which is 1.3 times 10 to the negative third molar. Ethan?
Never mind. I had a question, but I realized I was wrong. I thought there was a mistake, but I was wrong. No.
Okay.
I have a question.
Sure.
How did you get rid of the minus X underneath?
I just randomly waved my hand and said it's so small compared to this that I can ignore it because the Ka is 1.8 times 10 to the negative fifth, which is relatively small. This was an assumption we started making back in chapter 15, and it's usually pretty good. So now you always have to check and say, is 0.1 minus X equal to 0.1? And if we check in this case 0.100 minus 0.0013, we actually get 0.099. And 0.099, is that about equal to 0.1? It's good enough for me in this case. If you choose that that's not good enough, then you have to do a quadratic. And if you do the quadratic, you end up with this. You end up with X squared plus 1.8 times 10 to the negative fifth X minus 1.8 times 10 to the negative sixth is equal to 0. And then you identify your A, B, and C. A is 1, B is 1.8 times 10 to the negative fifth, and C is negative 1.8 times 10 to the negative sixth. And when you solve, X is equal to 0.0013 molar with sig figs, which is exactly the same answer we got not using the quadratic. So in most cases, when your K value is 1 point something times 10 to the negative fifth or smaller, you can get away with this. And so I usually do. Okay, there's one for you to try on the next page. So go ahead, do this one now, nicotinic acid, and again, it's okay to call it HA. And go ahead, do this on your whiteboards.